Okay, our next speaker is Matthew from Princeton.
Okay. Hello, everyone. I'm Matthew Molinelli from the Halk Lab at Princeton University. And today I'm going to be talking about a triangle ladder lattice for quantum simulation on superconducting qubits. Superconducting transmons are widely used as the building block of a quantum processor, but they also have much utility in analog quantum simulation. The transmon is formed by placing a capacitor and a Josephson junction in parallel, and they're characterized by their 0 to 1 transition frequency as well as their anharmonicity. For quantum computing, these properties allow the transmon to be used as a qubit with a well-defined 0 and 1 logical state. On the other hand, for quantum simulation, transmons can naturally simulate interacting bosons. We can couple many transmons together to form an interacting system that is described by the following Hamiltonian. The first term will count the number of excitations on each qubit, and the second term will take into account the anharmonicity of the transmon. The third term will allow excitations to hop between qubits due to the capacitive coupling. Interestingly, this Hamiltonian also describes the way that bosons interact on a lattice, where we can take a mapping for qubits to become lattice sites and microwave photons to become particles. One interesting platform to study Hubbard physics is the triangle lattice, due to the addition of geometric frustration. The interplay between frustration and strong interactions could lead to exotic quantum phases even beyond the superfluid and insulator phases. Previous work on ultra-cold atoms in optical lattices has demonstrated emergent phenomena that's apparent in this geometry, such as in this example, the existence of robust spin polarons that are correlated with hole and particle dopants in the lattice. Or in another example, tuning a square lattice into a triangle lattice to observe the transition into a frustrated spin liquid. Implementing a triangle lattice on superconducting qubits has the added benefit of giving us individual control over the frequency of each site, as well as coupling between sites. And we can exploit this tunable coupling to explore 0 and pi flux threaded through a lattice. In our previous work on rhombus lattice, we demonstrated the existence of an all-flat bands lattice for pi flux threaded through each plaquette. But in order to implement both 0 and pi flux, we had to do this geometric trick of rotating one of our qubits by 90 degrees in 2 separate devices. The ability to tune coupling within the same device would greatly simplify this experiment, and we could also be able to pick 0 or pi flux individually for each plaquette. To implement tunable coupling, we can add another tunable transmon in between our qubits. And in frequency space, if the qubits are coupled to the coupler with strength G, and if they're separated by a detuning delta, then the effective coupling will scale like G squared over delta, where the tunability comes from changing the frequency of this coupler. And we can achieve both positive and negative coupling by tuning the coupler either above or below the qubits in frequency. We can then imagine building up a triangle lattice with these couplers, like this. And if we ignore the coupler modes, then this effectively simulates the triangle ladder lattice shown here, with tunable coupling G parallel along the top and bottom edges, and fixed coupling G along the rungs of the ladder. You might notice that we've only included couplers along the top and bottom edge of this lattice, and that's because we can still achieve independent control over the flux through each plaquette with tunable coupling only along one edge of each triangle. And this is simply done by tuning this coupling to either positive or negative. Here's an image of our triangle lattice device. We have 5 qubits with 3 tunable couplers in this triangle lattice formation. Each qubit also has a readout resonator and a flux line for tuning the frequency of the qubit. And lastly, each coupler has a flux line to control the coupling. And if we zoom in, we can see the capacitor pads of the transmon, as well as the Josephson junction squid that shorts them here. The first set of measurements is to measure the coupling strength between our qubits. And this is done with 2-qubit swaps, where first we excite one of the 2 qubits and then quickly jump it onto resonance with the other with some detuning. We let this evolve for some time t, and then we read out the populations. We get this characteristic chevron pattern with detuning on the y-axis and time on the x-axis. And then we take the coupling strength to be the slowest swap rate at the center of the chevron at 0 detuning, which here is around 13 megahertz. We can tune the coupler frequency to see how this chevron pattern changes, and it's either faster or slower depending on what the coupling is. As a reminder, we planned this coupling to be both positive and negative by tuning the coupler either above or below the qubits, and this is in order to implement both 0 and pi flux. But as shown here, we cannot actually determine the sign of the coupling from these qubit swaps alone. So we need to do another kind of measurement to detect this. To detect the sign of the coupling, let's first consider the eigenstates of a 2-qubit subsystem, which shown here are separated by 2g and are given by these plus and minus eigenstates here. The energy ordering of these 2 states will depend on the sign of g. So we can imagine introducing a 3rd qubit acting as a probe to interfere with this 2-qubit state. Then, by preparing either the higher or lower state, we can determine the sign of the coupling by comparing the resulting dynamics. The experimental procedure will be similar to before, where first we are preparing one of the 2 qubits, but then now we are slowly ramping it onto resonance to adiabatically prepare the initial state. We then jump our probe qubit onto resonance and let this evolve for some time, and then read out the populations. First, if we prepare the higher of the 2 states, then for the case of positive coupling, we see coherent swaps between our probe qubit in orange here and the 2-qubit subsystem, which is shared by qubits 1 and 2. As a reminder, we can tune our coupling to be positive or negative. So now if we move our coupler below and go to negative coupling, we actually see no swaps. The probe qubit has no population for the whole time. If instead we prepare the lower of the 2 states, then this is the opposite. For positive coupling, we see no swaps. But for negative coupling, we see these coherent swaps again. And this matches our simulations. To get some intuition for why this happens, let's consider the case of positive coupling and preparing the plus state, which has equal population on the 2 qubits with the same phase. When we introduce the probe qubit, we see coherent swaps. If instead we prepare the lower state, or the minus state, then this again has equal population on the 2 qubits, but opposite phase. So they destructively interfere on the probe qubit, and we see no population transfer. This is a great example of geometric frustration, where the triangle shape leads to observable interference effects. In conclusion, we've demonstrated both 0 and pi tunable coupling within the same device, as well as individual control over the flux of each plaquette. And we've also leveraged this triangle lattice geometry in order to detect the sign of our coupling, and thus 0 or pi flux. Next steps would be to extend this idea of detecting the sign of coupling to longer 1D chains. And our system is nicely set up to be able to probe the eigenstates of a 1D chain of qubits with a set of ancilla qubits. And I'll point you towards a poster by my colleague Josh Wang tomorrow. Lastly, we'd also like to look at more interesting Bose Hubbard physics with this triangle lattice geometry and frustration. And this could be some bosonic quantum Hall effects, or even some topological phases in the triangle lattice. Okay, thanks for listening.
We probably have time for like 1 or 2 quick questions.
Okay, so is the